we go. All right, first of all, a property. What is a property? Tell your partner, what is a property? It's not a house, it's not real estate. A property is a characteristic, okay? Now there are two main categories of properties. There are physical properties. These are the most common. Especially in grade 9, when you make observations about things, only a few of those observations will be chemical, okay? We will do some labs where specifically we are doing chemical reactions. Why is this go away? What is happening? Okay, there we go. Sorry about that. Having a little computer issue. It's all good now. But most of the things, like if you were to observe anything like sitting on your desk, you would be looking at physical properties, because if you have a chemical property, you can only tell a chemical property if a new substance is formed. Why is it not erasing? Come on, there we go. Because a chemical property has to do with how a substance reacts, how it changes into a different substance. So if you burn something, that would be if something is able to burn, that is a chemical property. So if you take, just a regular old pencil, which I don't even have in my desk because I don't like the wooden pencils, but let's say you just take a wooden stick. Will it burn? Yes. So one property of wood is that it is flammable. If you take a rock, will it burn? No, okay, because it is not flammable. It won't change into a new substance. If you burn the stick, will you have a stick afterwards? Or will you have something different? You'll have something different. You'll have a new substance. You'll have some ash. You'll have some smoke. Something new was produced. So if you say something is flammable, in other words, burnable, that is a chemical property because you can only tell that if you actually burn it. Yes? If I take some acid and I pour it onto a piece of metal, if it is a strong enough acid, it will actually eat through the metal, okay, and leave a hole. So metals react with acid. So that would be a chemical property because it involves a reaction. Yes, we started out with the acid and a metal. You'll see some bubbles, things will happen. You'll be like, woo, reaction. Okay? What if I took some acid and put it on a plate of glass? Does anyone know what happens? Absolutely nothing. That's why we can hold acids in like a glass beaker. So if we say reactivity with acid, that's a chemical property because it depends on whether something reacts or not. So physical properties are the most common. Chemical properties are it's only a chemical property if it reacts and you get new substances. So a few ones that I wanted to look at here, and you can let me know any others that gave you trouble as well. I wanted to look at number 7, melting point. That's the temperature at which a substance melts. Tell your partner, do you think that is a chemical property or a physical property? Yes? You would say it's a chemical one? Not a bad guess. Yes? Physical? What would you say? You would say physical? Yes? Sorry? Physical? Okay. So let's think about something that melts, something that we're really familiar with. Ice. What is ice? Water. It's made of H2O molecules, and because it's a solid, they're arranged in a really regular pattern. Okay? I'm not going to draw too many of them because I don't have space. Okay? But you can imagine they would be stacked on top of one another like this. They would make like a nice little crystal structure. Yes? So that's my water. Now, if I melt it, what do I get? Water. Except that now it's not all organized like that and stacked and the molecules don't stay in place. Maybe I've got one here and it's moving this way, and I've got another one here and it's moving that way, and I got another one here and it's facing that way and moving this way. Okay, and so there's a lot more movement, but what can you say about all the molecules? Has anything happened to them? Are they different or are they the same as they were before? They're moving, but is their composition any different? Are they made of different things? No. So each molecule is identical to all the other molecules as it was before. So we have had a physical change because we haven't actually made a new substance. Okay? So melting point would be physical. Let's see, what other ones did I want to look at? Solubility. How well does it dissolve? Chat with your partner, decide is that one chemical or physical? Number 4. Okay, anyone want to give me an opinion on this one? Yes? I got a physical, chemical, chemical, physical, chemical. We got to split down the middle here, don't we? So it's got to be one of the two. So this one is actually, the dissolving is actually the trickiest one, okay, which is why I'm bringing it to your attention. So when something dissolves, let's just start with salt dissolving in water. Something we're all familiar with. You can all probably, if you have not done so, you could go home and take some salt and dissolve it in water. What does solid salt taste like? Salty, yes? Shocking. What does salt water taste like? It tastes salty. And that's because what we're actually doing with the salt when we put it into the water is we have a crystal and it's made of lots of smaller pieces, okay, atoms essentially. And what we're doing is we're breaking it apart into smaller and smaller pieces. We'll look at this in more depth later, but you break it apart into smaller and smaller and smaller and smaller pieces in the water, and then you mix the two together. But you still have salt, just tiny, tiny particles as opposed to like a crystal, okay? And you still have water. So you still have salt, you still have water. Is that chemical or physical? If you still have salt and you still have water, it's physical. Imagine if you took some salt crystals and you pounded them into tinier pieces. Would that still be salt? Is that chemical or physical? That's physical. Now, water can break salt into even smaller particles, so small that you cannot even see them, okay? That's why this can be really tricky, is that it's really hard to visualize things that are that small. But what happens is you would have salt, which is made of sodium and chloride stuck together, okay? And then we would dissolve it into some water. And the salt, the Na comes apart, the Cl comes apart, but we still have NaCl, they're just separated, okay? And all throughout here we have water, 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 water. Okay? It's tricky. If you don't understand it, you can always memorize that dissolving is a physical process. When you're dissolving a compound like salt, it's almost like a chemical process, but not quite, which is why it can lead to a lot of confusion, right? So technically, it is defined as being a physical property. Yes? Yes, so if I had sugar dissolved in water, in fact, sugar is even better because sugar is C6H12O6. It's got 6 carbons, 12 hydrogens, and 6 oxygens. It actually forms, each little molecule of sugar forms a little hexagon. Okay, you've got a carbon at each of the 1, 2, 3, 4, 5, 6 carbons. Okay, and then the oxygens and hydrogens are branching off of there, but we don't usually draw them. Okay, so let's imagine that we have a little crystal of sugar, which is a sugar molecule attached to another sugar molecule attached to another sugar molecule. I'm only going to draw 3 because it's too tiring to draw more. Okay, so this is my sugar crystal. When we dissolve it, when we put this into water, each little hexagon comes apart and is separate from each other little hexagon. But you still have this same molecule with the same shape and the same composition. So that's why that's a physical change. Okay, like I said, if that makes sense to you, that's fantastic. We will watch a couple of videos later on just to kind of give you the idea of what's happening there a little bit better. But that's why I wanted to bring up solubility. Solubility is physical. All right, were there any others that you wanted to take a look at? How about sour taste? Tell your partner what you think. Physical, we good with that? Yep, because you're not getting a new substance. How about boiling point? That's physical because just like when we had our melting point, we maybe, in this case, we're taking liquid water and changing it into gaseous water, but it is still H2O. You still have Mickey Mouse. Okay? Yes. Absolutely. There we go. Is that better? Yeah. Were there any other from that list, if you checked with the answer key, that you weren't sure about, that you were like, why was this chemical or why was this physical? Or were the rest of them okay? The rest were okay? Okay. You done? Okay, cool. Were we good with, let's see, flammability? What's flammability? Flammability is chemical, because if things burn, you'll end up with new substances. Yes? Okay. States of matter. These are little abbreviations for the states of matter. You've probably already heard of solid, yes? And we abbreviate it by putting a little s in brackets. That's a lowercase s. So if I wanted to say I have solid salt, I would say I have sodium chloride. That's made of Na, the sodium atom, and the Cl chloride atom. And I would put down at the bottom a little S, just like that, and say that's my solid salt. Liquid, I have a tendency to use that kind of an L just because it doesn't look like a 1. Okay, but you're welcome to use just an L like that. That's also fine. Okay, so either way, like that or like that. And so if we have liquid water, that's going to be H2O. So the little 2 goes down at the bottom. We'll learn all those rules later on about where all the little numbers go. They don't go at the top, they go at the bottom. And this one would have, beside it in brackets, we would write an L because it's a liquid. Gas is just represented by the letter G. So let's say we have helium gas. Okay, that's going to be He, helium. And then we're going to put a little G. Yes, yes. And finally, has anyone heard of this last one? Aqueous. Aqueous. Anyone heard of it? Nope, it's new this year. Perfect, that's great. It just means dissolved in water. So if you have salt water, you have NaCl, and then you would put bracket, and the symbol for that is AQ. That's different from liquid salt. Yes? Ooh, electricity is a plasma. And right now we're not going to focus on plasma. So plasma is where you have charged particles in a gas form. Okay? So electricity, it depends on what type of electricity you're talking about. If we're looking at the cathode ray is a plasma because it's in gas format. But if you have electrons and they are moving through a copper wire like they do in your house, then that would be in the solid form and you just have electrons flowing within that solid. Yeah? You can also have electricity flow in an aqueous solution of a salt. A salt will actually conduct electricity quite well, which is why if you drop the toaster into the bathtub while you're having a bath, you could die because there will be all sorts of little aqueous ions in there that have charges that will move and will carry electricity and you don't want to do that. I don't know why anyone would have a toaster, at their bathtub. But you know, maybe you're hungry. Make the toast first, then have the bath. Okay. You might also have sugar water. And so we would have C6H12O6. That's the symbol for sugar. Do you need to know that? No. You just need to know that if it is dissolved in water, we call it aqueous. So we have 4 states of matter. All changes of state are physical. So if you go from solid to aqueous, that would be dissolving. And that is physical. Okay, so we have all of our changes of state. We are going to go over this in a little more detail, but this just introduces to them. What do we call it when we go from a liquid to a solid? That is freezing. What do we call it when we go from a solid to a liquid? Melting. How about a liquid to a gas? Evaporation, or it could be boiling, either of those. And what about when the gas turns into a liquid? Like say on a cold morning on your windshield. That's condensation. Now there is a weird one. Have you heard of something that changes directly from a solid to a gas? Yes? But you've seen it, yes? Yes. Dry ice. Have you heard of dry ice? Okay, it's solid carbon dioxide, and it does not change into a liquid when it gets warm. It just starts producing a gas, and it actually, like, you know, goes off, and we're going to watch a video of that in a little bit. But anyway, so that process where it turns from a solid to a gas is called sublimation, and gas to a solid is called deposition because it's depositing. Okay, like I said, we'll go more into the depth there later. But if you go from solid to aqueous, what's that process called? That's dissolving. And that is a physical process. Did you have any questions from either this page or the next 2 pages? I realized after the fact that this flow chart is actually a little bit confusing because it says without changing it. It makes the yes sounds like a no and the no sounds like a yes. Do you know what I mean? Like when, I don't know. You can just ignore the flow chart. If you understand the difference between chemical and physical, you can just go with it and ignore the flow chart, which I think is flawed. It's correct, but it's hard to interpret. Any question from 54, 55, 56? We're good? Okay. So I think, never mind. We'll talk about that later. Okay. Let's go back and take a look at page 11. Page 11. Yes. No, there you go. I have a plan. Trust me, I have a plan. All right. Let's see if this works, this link here. Oh, it looks like it's working. Yay.
In this video, we're going to look at how scientists discovered that atoms have a nucleus in them. This discovery was made by Ernest Rutherford as well as his colleagues in 1911.
So, do you know the name Hans Geiger? Have you ever heard the name Geiger before? A Geiger counter. So he was a guy who studied a lot about radioactivity. Okay? This page again is what? Enriched material. So if you just want to sort of sit back and enjoy this, you can do so. But it does explain how they figured out that all of that positive charge was in the center and not all spread out.
And they made this discovery with their famous gold foil experiment. And we're going to talk about that here. So atoms. This is sort of how we think about atoms today, with electrons on the outside, and then in the middle, a dense, hard nucleus that's where the protons and neutrons live. But it wasn't always like this. Before Ernest Rutherford and his co-workers did their experiment, this is what scientists thought the atom looked like.
And who came up with this plum pudding model? Tell your partner. Who came up with the plum pudding model? If you're not telling your partner, you're not reviewing for your quiz next Monday. Who came up with this plum pudding model? J.J. Thomson, yeah. Even if you just said Thomson, or even if you just said J.J., I would know who you were talking about, okay?
They called it the plum pudding atom. Now, plum pudding is kind of a British thing. So if you're American, it might be better to call this the blueberry muffin model. Think about this. You take a blueberry muffin and break it in half. What do you see on the inside of that muffin? Well, you'll see blueberries, and the blueberries are just kind of randomly stuck into dough.
What charge are the blueberries? Oh. And what charge is the dough? Positive, beautiful.
And that is exactly what scientists thought the atom looked like at a very small scale. That electrons were sort of like blueberries, and they were stuck in this dough, kind of, that was positively charged. So you got this positively charged dough with electrons stuck randomly in it. This is the plum pudding model, but of course it turned out not to be true. Here's how Rutherford and his co-workers showed that the atom had a nucleus and that the plum pudding model wasn't right. They started out with a piece of gold foil, which is like tin foil or aluminum foil, except it's made of gold. I mean, wouldn't this be awesome to like wrap your sandwiches in for lunch? Anyway, I don't know, maybe if you're really rich, you use gold foil to like prepare your lunch. Anyway, they took this piece of gold foil and they shot tiny little things at it. What they shot at it were called alpha particles, which are tiny positively charged particles that are much, much, much smaller than an atom.
Okay, we're just going to pause there so you can fill in all of those boxes. So we have Hans Geiger, Ernest Marsden, and Rutherford. And this little alpha, you can draw like a little fish. Looks a little bit like a fish. Alpha is the Greek letter A, okay? Alpha, beta, gamma. Okay, alpha, beta is how we get the word alphabet. And so alpha particles are they big or are they small? Small. Are they positive or are they negative? Positive. Alpha particles are positive. Are they as big as an atom or smaller than an atom? Smaller than an atom. Okay. So that's what they're like. And certain elements, when they undergo radioactive decay, they spit out alpha particles. They just come out, and that's, Geiger would use his Geiger counter, and it would go pip, 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 if there was a lot of them, okay? And so those are alpha particles. So they knew that they could get alpha particles being shot out of an element that was radioactive. So they knew how to get alpha particles.
So they take the gold foil, They bam, 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 shoot alpha particles at it. Now they want to know what happens to the alpha particles after they hit the gold foil. So here's what they do. They take a material that flashes when it gets hit by alpha particles, and they take this material and they bend it around into a circle like this. So wherever the alpha particles hit, they'll see a flash. They take this material and then they take their piece of gold foil and they put it right here in the middle of the circle. So now they shoot alpha particles into the gold foil and they'll see a flash somewhere on the circle that will tell them where the alpha particle ended up after it hit the gold foil. Now here's what they see.
Now, if you were Rutherford and you were studying the material of J.J. Thomson and you thought, hey, this plum pudding model looks really pretty good, you can think of the alpha particle like a gun, okay, and you're shooting bullets at a blueberry muffin. What would you expect? Which direction would you expect the bullets to go? If my projector was the blueberry muffin and I shot it with a gun, okay, which direction would the bullet go after it hit the blueberry muffin? Yes? It would go through it because a bullet has much more structural integrity than a muffin. So it would just go straight through. It would not bounce off. It's not like I put, some Kevlar there or something like that. It's going to go straight through a blueberry muffin, okay? So that's what they're thinking is going to happen. Let's see what actually happened.
Most of the time, they shoot alpha particles, bam, 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 here at the gold foil, straight on, and they see flashes right here, behind the gold foil.
Is that where they would expect them to be? If they're going straight through the gold foil, let's follow that trajectory. Here comes an alpha particle. If it goes straight through, it would end up right there. So that's where they expected them to go.
So this would indicate that the alpha particles are going right through the atoms of the gold foil and are ending up over here. So that's the first thing they notice. The second thing is a really huge surprise. When they shoot the alpha particles every once in a while, they don't see a flash here. Instead, they see a flash over here, or a flash over here, or sometimes a flash here, or here.
So if we're going to see a flash here, if I shoot the alpha particle, what's going to happen to it to get a flash here? Yeah? It's going to have to reflect, it's going to have to bounce off, like ricochet, essentially, yes? So, and they're like, hang on, blueberry muffin, bullet, what the heck, right? Like it's a mystery. So they had to do some thinking about that.
Which makes them think that the alpha particles are hitting the gold foil and are veering off to the side once in a while. Or sometimes they're hitting the gold foil and they're bouncing back completely, all the way back. So, we can kind of summarize what they see using a diagram like this. Here we've got our circular detector screen that flashes. Here's an alpha particle emitter, which is just a fancy word for an alpha particle gun, something that's shooting alpha particles. Most of the time, these alpha particles hit the gold foil and they go right through, and we see flashes on the screen on the other side. But every once in a while, an alpha particle will hit the gold foil, zoom, zoom, and will veer off to the side and flash over here. And every once in a while, it will hit the gold foil and will bounce back almost 180 degrees. Flash here and flash here.
Okay, I'm just going to pause that, so if you want to fill in that little alpha. And what they've got here is they've got this alpha particle emitter. It's a lead box. They use lead because lead does not let radiation through it. Alpha particles are a type of radiation, and the lead won't let it through, okay? So you're not going to have alpha particles coming out the side or going out the back, anywhere where you don't want them. But they cut a little hole in the lead, and then that radioactive material, as it decays, it shoots out alpha particles. It's shooting them in all directions, but they can only get out the front because there's a hole there, okay?
So, Based on these two pieces of information, Rutherford and his team are able to make some conclusions about what the atom actually looks like. Here's the conclusions that they come to. Let's start with this gold foil, okay? The gold foil that they use is incredibly, incredibly thin. And in fact, it's so thin that these guys reason that there are only a few atoms in its thickness, that it's only a few atoms thick. So let's look at it on its side here and look at a magnified view of the gold foil. If we want to think about gold atoms as being sort of circles or balls, this is what the view from the side of the gold foil might look like.
And don't worry about copying this down yet. You'll be doing the questions later and you can fill things in, okay? Just watch for now.
It's 2 atoms thick here. Now, let's think about the results that they got from the gold foil experiment, okay? The first thing that they saw is that most of the time, the alpha particles seem to have gone straight through the gold foil. So, based on this information, they're able to reason that most of the atom is empty space. Or if there's something there, it's very light. It's not very dense, and it's really easy for the alpha particles to shoot right through. So most of the atom is probably empty space. But now the second thing they see is that every once in a while, an alpha particle zoom, veers off to the side, or it's like it hits the gold foil and bounces back. And so based on this information, they reason that while most of the atom is probably empty space, they think that there must be something very small but very hard inside each atom. And here's the drawing here. Of course, you know that this is the nucleus now, but they didn't know that the nucleus existed, so they had to discover it. And so they think there must be something really, really hard. And when an alpha particle hits it head on, bam, that alpha particle's gonna ricochet back. And they also notice, as we said, that sometimes the alpha particle veers to the side. They say, well, maybe it's because it hits the nucleus on the side of it, so it goes off like that. Or they also said maybe since alpha particles are positively charged, maybe the nucleus is positively charged. So that if the alpha particle comes close to it, remember, things that have the same charge repel each other. So you've got this alpha particle coming close to a positively charged nucleus, then zoom, it's going to veer off to the side because they're pushing away from each other.
Did you guys get that? What charges the nucleus? Positive. What charges an alpha particle? Positive. What does positive do to positive? They repel. So when an alpha particle gets really close to, like let's say here's my nucleus, here comes the alpha particle, what's going to happen if it comes close by? It's going to get pushed away, and that's why it can veer off to the side. Now, if it happens to hit it straight on, it might bounce back. But if it comes close, it's like, ooh, I don't like you, you're positive, so I'm going to move away. All right, and that's how they can end up veering off to the side. And that's what let Rutherford know that there was something, but it had to be very, very small. Why couldn't it be big? What would they have seen if it were big? Yes? Yeah, you would not see all the alpha particles going through. If you had something very dense and very big, they would just bounce back. So they knew that it had to be very, very small. But most of the rest of the atom, what was the rest of the atom? Mostly empty space. I mean, there are electrons there, but like they're zooming around. They're not in any one space for very long, right? So most of it's empty space with just like a couple electrons zooming around in there.
So regardless, based on this information, they reason that there is something small and hard in the atoms that once in a while the alpha particles are banging into, and that's what's causing them to bounce back or to veer off course. And they also reason that whatever this nucleus is made of it's probably positively charged because of the way it looks like the alpha particles are sometimes getting repelled and pushed away. So if you take these two pieces of information together, we can come up with a model for the atom that looks like this, where this is just a combination of those two things I saw, where we've got these gold atoms lined up, and most of the time, if alpha particles pass through so they don't hit any nucleus here, they just go straight on through. But if an alpha particle hits this hard, dense nucleus, or is close enough to be repelled by its charge, it veers off or it bounces back. So here's how the gold foil experiment changes how scientists think about the atom. Okay, so as we said before, here's a plum pudding atom with these electrons stuck in a positively charged kind of pudding. But Rutherford's experiment shows that this isn't quite true. Instead, he comes up with a model like this, where there is a hard, dense nucleus in the middle, and that is where the positive charge is. So the positive charge isn't like this kind of blueberry muffin dough that's spread throughout the atom, but instead the positive charge, everything that I've drawn in red here, the positive charge is concentrated right here in the middle of the atom, and then there might be some electrons floating around on the outside.
What's the name of this model? We got the Rutherford atom, but it's also known as the, starts with an N, nuclear model, because it contains a nucleus, okay?
They're certainly not held in place because of the positively charged dough. Now, this is just one piece in a puzzle of figuring out what the atom actually looks like. So shortly thereafter, Rutherford comes up with this model for the atom, but then scientists realize that the electrons probably aren't just stuck in place, and instead they think that the electrons are spinning around the outside of the atom, and you still have this hard, dense nucleus in the middle. And then only a short while after this, it's discovered that the nucleus isn't just a hard piece of positive charge, but that the nucleus is actually made of protons, each one of which has a positive charge, and then the electrons are spinning around the outside. Now this is what we call the nuclear atom, because it has a nucleus. So we've got the nucleus of protons, and then electrons spinning around the outside. But of course, you probably know this still.
What is missing from this nuclear atom so far? We got protons in the middle, we got electrons on the outside, bam. Yeah, we're missing the neutrons, okay?
Isn't an accurate representation of exactly what the atom looks like. In fact, they're totally missing the neutrons. It wasn't until the 19th.
So the reason we need neutrons in the nucleus, what does a positive charge do to a positive charge? They repel. So can you imagine trying to cram a positive proton and a positive proton together into a very small space? What would they do to one another? They would repel each other. So there is an electrical force trying to push the protons apart in the nucleus. But the neutrons provide a different force about which I know hardly anything because it was not part of my high school or university education because I only took first year physics, not second or third year. But there's another force in the nucleus of the atom, and the neutrons provide it. And it is stronger than an electrical force. And it glues, it's almost as though the neutrons glue the protons together and keep them from repelling apart. Okay, it's called the strong nuclear force. Like I said, you don't need to know anything about it, but if you were ever wondering, like, how do you get all these positives crammed together so close together? It's because the neutrons glue the protons together, okay? And I think we're just gonna leave it there for now. You can work on pages. Now, 11 and 12 are enriched. So actually, I'm gonna just give us a new page here. And so I'm gonna write down the pages that are the enriched stuff and that are the regular stuff. Okay, so the enriched stuff is page 11 and 12, so that's optional. Regular, page 13 is for everyone. Page 14 is enriched. That involves the Rutherford and cathode ray tube experiments. And then page 15 is regular. And I think there might be one row too many. Maybe one row too many. So if you're like, there's like 6 rows and I only have 5 models, don't worry about it, just leave out a row, okay? I'll fix that in my next edition, okay? So that is your homework plus these if you are doing that. If you are finished and would like to do some more enriched stuff, 2.1c, pages 28 through 32. Okay, and this is Chadwick discovering the neutrons, and I'm not actually gonna go over that one with you guys. Okay, so for most of you, this is what you're working on. If you did not finish the reading check on page 25 and the reading check on page 20, make sure it's complete. There's going to be a quiz next week on the models of the atom. Quiz Monday. You need to know the name of the model. You need to be able to draw a labeled diagram. You need to be able to give the name of the scientist. And finally, you need to, if you're doing the enriched stuff, you need to know about the experiments and be able to answer some questions about the experiments. Okay, so the bulk of your homework, you might even be able to finish it in class today. I'm giving a little extra time though because I'm going to be giving back your tests and I know you'll want a chance to take a look at them, okay, and ask me questions about it. So there's the regular homework. This bit here is just if you haven't finished it already, okay, most of you have. And if you want to, you can start studying for your quiz on Monday, all right? I'm going to grab your tests and get those back to you so you can look over them. By the way, if you'd like to check out all your marks and make sure I've entered them correctly, you can go on to my ed and check it out. The only thing I've not entered so far, nothing to do with the labs and not the enriched stuff from the test. Yes. Yep. Yep. There's actually lots. No, he's just like a same principle. You don't necessarily. You're not going to get your Scantron sheet back with it. What I've done is I've circled the questions, multiple choice questions that you got wrong. Okay? When you are done looking at this, I need it back from you. If I don't get it back, what do you get on the test? 0, which would suck. So make sure, what do you do when you're finished with this? Give it back. Did you fall in? Sorry, you were going to fall in all the time. Yeah. When you're handing your test back, you can just put it in here. You can put it face down if you don't want anyone to see your mark or whatever. Keisha. Sorry, Rehan, you had a question. Michael.
Which one was this one?
That one is true. That one is the one that we can
Oh, you used that.
Hi. I know I got a 91.2.
Yeah.
And yeah, this you okay, I'm just wondering, it feel like mocking. You know how some teachers will do like 30 to 20, that's like developing. Does proficient go up to 95 to 100 or
Proficient goes up to like 95.
so close.
I know, you're so close. It's all good though. Okay?
What'd you put then? I don't even know. What did you put? Where is it?
Thank you. Ladies and gentlemen, if you got less than 75%, you can come in during flex, or you can come in after school to do some more learning with me. We'll go through, we'll do the corrections, and we will improve your grades. So if you're sitting down there below 75% and you're like, dang, I feel like I knew more than that, we're going to come in, we're going to have a conversation around the questions where you didn't score 100%, and you know, you can improve your grade that way. Okay? That's going to have to happen by the end of next week. This is not something that's going to go on forever and ever. Finish this by next Thursday, because Friday's off, holiday. Not this Friday, next Friday. It's a protein. Holiday for you guys, I get to work. When you're done, Let's see, did I add it? That's always possible. You know, I do my best, but there's like 60 of them and stuff. Okay. So we have 11, 17, 23 and a half. That's because this is not out of 8, this is out of 12. Thank you for checking. You're like, why? Why? That's a 12, so that's going to add 4 to your mark. There we go. When do you get to what? Well, I will, but I need a calculator to do that. So I'm just putting a star here because that means I need to be recorded. Okay? Then you don't. You look so, like, what are you going to do with it? Frame it? Put it on your wall? You keep all your tests? Well, you know what? At the end of the year, love, at the end of the year, I'll give it to you. Okay? So, Michael, disappointed? I guess. Okay. Hi.
It's only like chemistry extra books. Ooh.
touch this inspector?
You will towards the end of the block. Not at the beginning of the block.